That was nice. Okay. Welcome back, everyone. So today we're going to make a video on the following result, and just keep in mind we're working in the following metric, r with the standard metric, so the standard distance. This is important because this only holds in r because r is complete. Anyway, we won't go into the specifics of that, so let's just focus on this result. We kind of have built up to this result by proving the Bolzano-Weierstrass theorem, most importantly, and so now we're ready to prove it. We also discussed Cauchy sequences, and so that develops all of the prerequisite material to cover this. So we begin with the easier direction, which is the reverse direction. So let's consider that. That is, suppose a sequence a sub n converges. Let's say it converges to L. Suppose a sub n converges to some L, which is in the real numbers. Okay. So by definition, for all epsilon greater than 0, there exists natural number capital N, natural number such that well, n greater than or equal to capital N implies, I'll write it back down here, implies that the distance between a sub n minus L is less than epsilon. In preparation, we're actually going to use epsilon over 2. This is a standard trick if you kind of suspect. I mean, it would be fine if we left it as epsilon, because then we could continue with the proof and then we would realize that this would be helpful, but now I'm just doing this in advance so we could save some time. The idea is, again, we're going to apply the triangle inequality somehow, and we're going to get 2 epsilons over 2's, which combine to epsilon nicely. So that's the idea. Now we want to show it's Cauchy, so we want to introduce some kind of m here. So let m be greater than capital N. Then we have the following. So this is what we want to analyze when we're talking about being Cauchy, a sub n minus a sub m. Notice our criterion are satisfied, that is that we have m and n that are both greater than or equal to capital N. So this is equal to, we're going to add an L here, a sub n minus L plus L, and we're going to do it like this. So we're going to use parentheses, plus L minus a sub m. This minus sign doesn't really matter. We're going to use the triangle inequality and just take out a minus sign. So this is less than or equal to a sub n minus L plus a sub m minus L, and these are both less than epsilon over 2 for all n and m greater than or equal to n, and in general we'll just get that this is less than epsilon. So that's exactly what we needed for this this reverse direction, so I'm just going to put a check mark. Now I'm going to clear the board and we'll get to the next direction. Okay, so now let's consider this forward direction. That is, let us suppose that some sequence is Cauchy, and then we want to show that it converges. So suppose, again, we'll use a sub n is Cauchy, that is, well, let's just write out the definition of being Cauchy. We have that for all epsilon greater than 0. You kind of know the business here. I won't say everything. There exists capital N, natural number such that n greater than or equal to n implies, m and n greater than or equal to n, capital N, implies that a sub n minus a sub m is less than epsilon. So these terms get closer and closer to one another. Okay, so how do we start here? Well, since we hinted at using the Bolzano-Weierstrass theorem, we want to kind of get to a point where we have a bounded sequence. Okay? So let's try getting to that. Well, how could we make a bounded sequence? Well, why don't we prove that this is bounded? And to do that, we're going to fix epsilon to 1. So fix epsilon equals 1. This is fine, right? Because then we can find, again, this holds for all epsilon, so we can find a capital N such that this holds. And we're also going to let m be equal to capital N. And this is valid, right? So we have the following. We have a sub n. I should write, so for all n greater than or equal to capital N, we have the absolute value of a sub n minus minus a sub capital N is less than 1. And so that implies that if we just consider the absolute value of a sub n, and indeed we're trying to bound it, so let's see what we can do here. This is equal to the absolute value of a sub n minus a sub n plus a sub n, again adding a 0 there. So establishing parentheses here, you can use the triangle inequality, and then use this here to show that, well, maybe getting rid of that. This is less than 1 plus absolute value of a sub capital N. I went through that kind of quickly because we've actually done pretty much analogous process in proving that in a previous video that convergence implies boundedness. So this is pretty much similar. And there's also this next step of, this last step, it's kind of technicality, of considering the set of all the absolute value of all the terms preceding a sub n, preceding a sub capital N, so a sub 1 through all the way to a sub capital N minus 1. And then you just, again, take the set with the absolute value of all of those, then you take the maximum of that, and then take the maximum of this term and that term, and then we get the bound that we want. I'm not going to write that all out since we've done that in the previous video, so I'm just going to write that as ... and then that's all going to imply that a sub n is bounded. Okay. So now we have that a sub n is bounded, so what can we do? Well, again, we use the Bolzano-Weierstrass theorem. Technically, we might want to convert this sequence to a set of all the values of that sequence in order to construct the subsequence, but we needn't worry about that. Yeah, so we have a subsequence with which converges. Okay, so let's let that subsequence be denoted by Bolzano-Weierstrass theorem. I'll just write about by that. Find a sub nk which converges to some L. Okay, again, and the real numbers. Okay, nice. So by definition, we're going to use this epsilon over 2 business. Yes. So for all epsilon greater than 0, there exists a natural number capital N. I'm just going to go through this quickly, such that lowercase n implies that minus L sub k minus L is less than epsilon over 2. Again, foreseeing what we're going to do in the future. This will be useful. So we also have that, well, using this fact that n sub k is going to be greater than or equal to, it's going to be greater than or equal to n. Okay, that's the fact that this is a subsequence. Okay, then, well, also for all n greater than or equal to capital N, I guess I should be careful here with using this stuff. So capital N here, I'll say this is n1. This should be n2. You got to be careful here. Okay. Also, we have this result. So this here, but then applied to m equals n over k. I'll just use, yeah, n1. Also, we may I'll just denote this result here, this result here, and then we'll transpose it down here. Implies, what am I doing here? Also, yeah, I'll just write, there exists, I'll just summarize it. Natural numbers such that for all n greater than or equal to n, we have that a sub n minus a sub nk is less than epsilon over 2. This is a bit different. Again, we're just using this epsilon over 2 case. This doesn't really mean anything. So we can find an n1. This is technically, let's use n prime here. This is going to be different because we have this epsilon over 2. Okay. So how could we use this? Well, let's see. Maybe again use the triangle inequality. So we're going to have that the absolute value of an minus L, we want to show this is less than epsilon, well, adding in that 0 here, minus perhaps a sub n minus a sub n k plus a sub n k minus L, so establish parentheses. Now this is less than or equal to absolute value of n minus n a sub n k. Taking out that minus sign gives, we don't even need to take it out actually. Okay, a sub n k minus L, and this is less than epsilon over 2 plus epsilon over 2, so less than epsilon. So what have we shown? We've shown that, and actually I should be careful here, this is for n greater than or equal to capital N, which is going to be defined by the maximum of n1 and n2, right? Because this holds for all n greater than or equal to greater than or equal to n1, and this holds for all n greater than or equal to capital N2. And so if we take the minimum, then we account for both of these, and then we can do it as such. Thus we found the capital N such that for all lowercase n greater than or equal to that, this holds, and that's just the definition of the fact that a sub n converges to L, and thus we've shown that sequence is Cauchy implies it converges. So that completes the video. I hope you enjoyed it.